Thank you very much. It's a pleasure to be here, even though it's only remotely. I have had the fortune to visit Brazil in the early 1980s because my uncle was actually working there for a number of years on a development cooperation with Brazil. And it was the most exciting trip for me as a young student to visit him in Brazil and travel to some of the projects he was collaborating with there. Today, I want to tell you a little bit from the point of view of natural science about what climate change will cities face and what it means to them, and also talk a little bit of their role in mitigating climate change. So without further ado, let me jump straight in. One thing everyone knows, of course, but it I think is still worth repeating, is that we are in the middle of a massive increase in carbon dioxide concentration in our atmosphere. Here you see the last 10,000 years of this, a very steep increase. You can also see, if you look at the numbers, the year numbers there, how this has accelerated. And we now know that the amount of carbon dioxide in the atmosphere is higher than any time in at least 3 million years now. And of course, we know that we are causing this increase in CO2 completely to 100%. And we know what it does in terms of physics, in terms of the energy balance of our planet. It leads to a heating of 2 watts per square meter of Earth's surface around the clock, 24 hours a day. And this is why it's getting warmer. We are simply adding heat to the system. And the result is shown in this nice diagram. Most of you have probably seen it by now. It's the famous warming stripes. This one shows the temperature of every year, the global temperature starting in 1880. This is the first line on the left, going up to last year from the NASA data. This is a more conventional way of showing it as a data curve, but I think the color stripes, the warming stripes, are a particularly impressive illustration of the exceptional warming trend we are still in the middle of until we stop it. This warming has been already shown very clearly is completely human-caused. The IPCC fifth assessment report included this nice diagram comparing the observed amount of warming to the human-caused amount of warming. And the human-caused is, of course, within the error margins, it's the same, but probably even a little bit more than what we observe. That is because natural factors of climate change have actually caused a slight cooling, slightly offsetting some of the global warming that humans have been causing. And of course, the key reason for that is that solar activity has gone down since the mid-20th century, which by itself would have led to some very small cooling of the planet. So global warming is what the science can say now is approximately 100% human-caused. And we also know how exceptional the modern warming is in terms of the natural climate variations. I'm actually a paleoclimatologist. I have been working on ice ages since the 1990s, and we can now simulate in our global climate model all the ice ages of the last 3 million years, just driven by the changes in the Earth orbit, which are well known, the so-called Milankovitch cycles, which are causing these natural climate changes in the last few millions of years. And the last ice age reached its maximum about 20,000 years ago. And you can see here the warming into the Holocene and the fairly stable Holocene climate, which allowed Homo sapiens to thrive, to build a civilization, to start agriculture, to build cities, and so on. And temperatures now in the globe are already very likely higher than any time in the Holocene and thereby in the history of Homo sapiens. Now, what does this mean for us? What we mostly notice, of course, is not the average temperatures, but what we feel is the extremes. And of course, as the globe warms up, we get more heat extremes. We have done a study a few years back looking at how many monthly heat records appear in the world, like hottest August in Germany or similar records anywhere in the world. And we have found that the number of monthly heat records is now 8 times larger than it would be in a stable climate. So that is a very striking illustration of how this, at first sight, maybe moderate sounding change in global mean temperature, this bit more than 1 degree warming, how that affects the number of heat extremes, of record-breaking heat extremes that occur. And of course, you have to realize that every new heat record has to beat all previous records. So the absolute temperature level for each of these records is going up and up each time it is broken again. And an example of such a heat record in Europe has been the European heat wave in 2003, which caused 70,000 fatalities. I will talk a little bit more about heat mortality later on when I talk more specifically about the impact on cities. Let me just add that in Europe, we can reconstruct summer temperatures going back to the year 1500 AD. And the hottest summers in Europe since then have been 2018, 2010, 2003, 2016, and 2002. And you don't need to hire a statistician to tell you that this has nothing to do with a random distribution anymore, but it is simply an effect of global warming. Another type of record that is increasing with global warming is rainfall records. And here we have done a statistical analysis of the number of daily rainfall records that we observe, which can cause flash flooding in cities. I'll get back to that later as well. And you can see here, first of all, in the gray bars, the every single year, the number of daily rainfall records that are broken on the planet from very long rain gauge records. And the red line is a kind of smooth line across those. Of course, there's a lot of variability in the number, but when you smooth that, you get the red line. And in a stable climate, this red line should be within the blue band that you see there. When it moves out of there, it becomes statistically significant, and that happened in the 1990s. The number of daily rainfall records has been elevated in a significant way since then, and it has been ever increasing since then. And these events can cause quite massive damage. Now, the opposite of too much water is drought, of course, and we have long expected, and we also observe an increase in drought in many regions. In Europe, this is primarily the Mediterranean region, which suffers from increased drought problems. But actually, it applies also to Germany. But what is shown here is actually winter rainfall data. In winter, we don't have such drought problems in Germany, but the Mediterranean has. The winter rainfall usually feeds the water in for the soils for the agriculture season. And these data show how the winter rainfall amounts have decreased in the last decades. And one of the examples, of course, that is affected by this in the Mediterranean area is the country of Syria, which suffered the worst drought in its history in the years up to 2011, when the mass protests and civil unrest there began. We all know how this ended. And there is good studies on this, like this one in the Proceedings of the National Academy of Sciences, which look not only at how this kind of drought has been greatly increased in likelihood due to global warming, but also how the effects of this drought have led to many internal refugees in Syria, farmers that left their villages and gathered in the suburban areas of Aleppo, of Homs, etc. And it was just increasing unhappiness with the Syrian regime, which then contributed to those mass protests. This is actually something that in the German Advisory Council on Global Change that I worked with for 8 years, we already warned about in a report, Climate Change as a Security Risk, which you can still download. It was published in 2007. And we looked at the problem of fragile states being affected by extreme events, droughts, harvest failures, and this leading potentially to internal conflict and ultimately failed states. Of course, you can never predict where this kind of thing happens and when, but it is a typical scenario for climate change as a security risk that we wrote about a few years before this happened in Syria. Another extreme event type that also affects many cities is the increase in tropical cyclone intensity. And I have been also participant in this very long-standing debate in the scientific community whether the expected increase in tropical cyclone intensity that is simply expected from the laws of physics, because warm ocean waters are the energy source for these storms, and we know the ocean waters are warming up as a result of global warming. So whether this expected intensity increase can be shown in the data, that was long debated because the observation systems have changed, and in the early days, many decades ago, of course, we didn't have satellites, we didn't have full data coverage, so storms might have been missed. But in the meantime, the special expert group by the World Meteorological Organization on tropical cyclones has diagnosed that tropical cyclones have increased in intensity, and it's a recent study published last year by Jim Cossin and colleagues using only homogenized satellite data from 1980, where we really have good data quality and we're not missing any storms, that there is a very clear increase in the share of major hurricanes out of all hurricanes, and therefore in the tropical cyclone intensity. Now let me talk about how this all affects cities and the role of cities in this. And of course, one thing which exacerbates the heating, the increased number of heat extremes that I mentioned, is the urban heat island effect. That's already for decades, of course, a well-known effect. Currently, the number of heat days in city centers, in urban areas, are about twice as much as in nearby rural areas. And in the future, this is expected, of course, to increase this problem of overheating in the urban centers quite significantly. In the extreme case of the RCP 8.5 warming scenario, the number of heat wave days can even increase up to a factor of 10 in urban areas. And I mentioned this European heat wave, which basically back then the city of Paris had to set up tents on the outskirts for all the coffins because there was such increased mortality. And you can see that in this data statistics, which shows the annual cycle of mortality in France for the last 20 years. And the year 2003 is the blue curve. And you can see how in August 2003, there was this massive spike in mortality where it was increased, it more than doubled compared to the normal mortality in summer in France. In France. And well, this is a massive spike, even compared to the one by the corona pandemic, which is shown in the red curve. That's the 2020 curve, the red one, where you see the first wave and the second wave of corona in France. And of course, the corona pandemic is longer lasting than that heat wave. So overall, the number of deaths is greater due to corona than due to the 2003 heat wave. But the intensity of the mortality peak there, the height of that spike is actually greater during the heat wave. There's a more systematic investigation of temperature-related mortality, a very nice paper by Gasparini et al. In The Lancet in 2015, where my Potsdam Institute colleague Veronika Huber is also involved as a co-author. They have done this analysis for many cities. I'm showing the example of Sao Paulo here for obvious reasons. And the top curve shows the mortality, and on the x-axis you see temperature, and the histogram at the bottom shows just the frequency of how often certain temperatures appear. So you see quite often the temperature in Sao Paulo is between 20 degrees centigrade and 25 degrees centigrade, and very rarely exceeds 29 or so, and very rarely less than 10. And so if you fold this frequency distribution of temperatures into the mortality curve, you get the kind of total number of deaths. But the point here is that mortality increases both for cold temperatures and for warm temperatures. The optimum, the lowest mortality, is between roughly 18 and 25 degrees centigrade. Now, that it's higher below that is not because people actually die from the cold directly. This is mortality from all reasons. You know, you could die from the flu, for example. It would go into this statistic if the people die from flu more often in cold weather than in warm weather. So mortality from all causes does depend on temperature. And if you look at this picture, you could get perhaps the impression that if it gets warmer, less people die from cold, more from heat, and this all balances out. Or some climate skeptics have even claimed that we will save more people from less cold than will be added from more heat. But that's actually not true. The reason is that the increase with heat, this rate curve there, is much steeper than the decrease with temperature if you shift the temperatures to the right towards warmer areas. And a newer paper by Gasparini and colleagues in 2017, again in The Lancet, has examined this in more detail, how much added heat mortality and how much reduced cold mortality you get in a warmer climate. Shown here 4 different warming scenarios, and on the left is South American cities, 22 locations, and the right is Southern European cities. And you can see the red bars are generally bigger than the blue bars. That means the excess mortality from heat is greater than what you save from reduced cold mortality. So this skeptic argument doesn't hold. More heat is actually bad in terms of direct health impacts on human mortality. Another problem that affects cities is that increase in flooding. This has actually 2 reasons. I mentioned the increase in extreme rainfall events already, but there is a second reason, of course, in coastal area, also linked to tropical cyclones in the areas prone to that. It is coastal flooding from storm surges. Both are increasing. The rain-fed flood events are increasing, of course, because extreme rainfall is increasing. That has simple physical reasons. Warm air can hold more moisture, which can rain down then in a rainfall event from saturated air masses. And the increase in coastal flooding has a double reason. One is, of course, the rising seas. Sea level is rising, has risen already about 20 centimeters in the last 100 years globally, and that increases storm surge risk quite significantly. For example, for Hurricane Sandy that hit New York, it's been shown that a major portion of the flooding costs can be attributed to the higher sea level. And it, of course, increases also by this increase in storm intensity, tropical storm intensity for those areas that are in the tropical storm belt. And there's an additional effect. Tropical cyclones have actually slowed down in their forward movement, and so they linger longer over certain cities like Houston, for example, in recent years. And that also increases tropical cyclone-related flooding, which in case of tropical cyclones comes both from the storm surge and from the massive amount of rainfalls. There was a record rainfall event with Hurricane Harvey in Houston a few years back. Rainfall, staggering rainfall amounts that had never been observed in the United States before. So cities have to deal with this. Berlin is building huge caverns to take up floodwaters for extreme rainfall events, to just store them, and similar things that cities have to think about to adapt to the increasing flood risk. Cities also have a major role in mitigating climate change, and this statistic shows you how the building of cities is also very important. In 1950, the urban fraction of the world population was only about 30%. That translated into 0.8 billion people. In 2015, it was already more than half. People lived in cities, and that translated into 3.8 billion people living in cities. And so between 1950 and 2015, buildings for people living in cities were built at a rate of almost 500 million people per decade that entered cities. Now, in the future, up to 2050, we expect the urban fraction of the world population to increase to 66%, which means that by then about 6.5 billion people will live in cities, almost twice as many as today. And the rate of construction of urban living space will be much greater than in the past. It's about 0.74 billion people per decade that need to be finding housing in cities in the future. And this is, of course, a massive building effort that goes on there, which is going to have a massive CO2 footprint unless it is done in a more sustainable way than building with concrete. And one important opportunity here is building with wood, because it doesn't only release much less carbon than building with concrete, it actually can store carbon. Of course, trees take up CO2 from the atmosphere when they grow, and the carbon is stored in the wood. And if you prevent this wood from decaying and store it for the long term, for a century or more in the form of wood buildings, then this is an important carbon sink that you can create there if you build with wood instead of concrete. And I have here some projects. This on the right one is a very high tower that hasn't been built yet, but it is planned in Tokyo. So it is possible to build even high-rise buildings from wood. There is one in Norway existing already now, which I forgot exactly how many stores it has, I think around about 20. And this apparently can be extended to much higher high-rise buildings as well, this building technique, and makes, by the way, also for more pleasant, more livable buildings. Let me finish by pointing out what is actually demanded from cities by the Paris Accord, which has the goal of holding the increase in the global average temperature to well below 2 degrees. Never forget the well below. Above pre-industrial levels, and to pursue efforts to limit the temperature increase to 1.5 degrees above pre-industrial levels. And the key question is here, what does this mean in terms of emissions? And I've made an updated diagram for that. We published the original a few years back in Nature together with Christiana Figueres and others. And it shows the observed global CO2 emissions in the black curve. And the 3 colored solid lines show emission budgets that would give us a 50% chance to stay below 1.5 degree. Notice how steeply emissions have to decline for this. And this is without assuming net negative emissions in some distant future, which many scenarios have, which I think is very unlikely to ever be realized. Of course, there is a bit of a debate in the scientific community about this, but the natural scientists that I know generally do not believe in any sizable net negative emissions in the future. And in any case, it would be putting off the problem of the emissions to the next 2 generations and tell them they have to clean up the mess and have to find a way of getting the CO2 back out of the atmosphere. The German highest court has just ruled that this is not allowed, to just shift the problem to the next generation, so to speak, kick the can down the road. The government actually has to do its share of the Paris Agreement now in the foreseeable future, and not pretend that after 2050 we can produce a lot of negative emissions. And so if you do that, then you need to, well, let's put it that way. If we had started right after the Paris Agreement in 2016, we would have been able to ramp down emissions like in the green curve to 0 globally, just close to 2050. But just by waiting for several years and continuing with high emissions, and I assume 2021 will have similar emissions as 2019, the COVID blip will be over, then we have to already reach 0 much earlier. Because the key for the amount of global warming is the area under the curve. It's the cumulative emissions which cause global warming because of the long lifetime of carbon dioxide in the atmosphere of tens of thousands of years for a large portion of what we emit. And so if we wait another 10 years or so before we start reducing emissions, then we will have to go down to 0 within 10 years, which obviously is impossible. And that is why it is so urgent to immediately start reducing the global emissions right now and not delay even 1 more year. So with that, I'm finished, and I thank you very much for your attention, and I'm very happy to discuss with you and answer your questions. Thank you.